Greetings, my young Padawans. This is Chapter 3, Section 3.3, and today we will be talking about the product and quotient rules when taking derivatives. So last class we talked about a lot about taking derivatives of basic functions, and we talked about the sum, we talked about the difference. Unfortunately, when we have the product of two functions, it is not the same as just taking the product of the two individual parts. Instead, we have to follow a slightly different process. So, for the derivative of the product of two functions, you take f of x times g prime of x plus g of x times f prime of x. I find that rule hard to remember, so instead, I simply remember the first times the derivative of the second, plus the second times the derivative of the first. I'm going to demonstrate in a couple examples. Okay, here we have the product of two functions. You'll see one of the functions is 4x plus 3x to the fourth power, and the second function is 2 minus x. So we're going to go through and we're going to take the derivative of this. So f prime of x, the derivative of f, is equal to the first. Okay, the first is 4x plus 3x to the fourth times the derivative of the second. The derivative of the second, the derivative of 2 minus x. Well, let's see here. That's just going to be -1 because of the constant that's in front of that. Okay, so there's the first times the derivative of the second plus, let's see here, the second, okay, that's 2 minus x times the derivative of the first. The derivative of that is 4 plus 12x to the third power. So with the first times the derivative of the second plus the second times the derivative of the first. And now we just have to simplify. So I will distribute through my -1, and then I will FOIL the second part. And now I will combine my like terms. And now I'll end up with my final answer of -15x to the fourth plus 24x to the third minus 8x plus 8. Let's try another one. Sometimes our functions can be in disguise, but you have to recognize this is the product of two different functions. We have x, and we have e to the x. So we'll go ahead and calculate the derivative of f by taking the first times the derivative of the second, and the derivative of e to the x is just e to the x, plus the second, e to the x, times the derivative of the first, which is 1. I'll simplify that, but there's really honestly not much to do. You have x times e to the x plus e to the x, and that's going to be my final answer. Sometimes your book may get fancy and factor out the e to the x, and you'll be left with e to the x times the quantity of x plus 1. It will really depend on the way the answer key may be written. Let's do another one. Actually, rather than me do another one, why don't you pause the video right here and give this one a try? Go ahead, pause the video and try this one out. Okay, so again, you will see you have two functions, 4x to the third power and the cosine of x. So as we calculate the derivative, we will again do the first times the derivative of the second. Remember, the derivative of cosine is negative sine of x. Don't forget that. Plus the second times the derivative of the first, which is 12x squared. All right, and we'll just simplify this down. We'll write it kind of together here. Let's see here. So I have -4x to the third sine of x plus 12x squared cosine of x. A lot of times we can't combine like terms like we could with the first problem. All right, let's try one more. Again, this, okay, so recognize where we have to use the product rule and where we don't. So the product rule has to be used here with this first part as we have the product of two different functions. But this second part, 3 cosine of x, that's its own little separate thing. Okay, so we'll calculate the derivative. Let's see here. So we have f prime of x equals, let's see here, we'll do the first, times the derivative of the second, cosine of x, plus the second, sine of x, times the derivative of the first, that's just 1. All right, that's the first part. Now we'll deal with the derivative of 3 cosine of x, which would be 3 times negative sine of x. And now we'll just simplify this down. So let's see here, I'll have x cosine x plus the sine of x minus 3 sine of x, And here there's actually a little bit of simplification we can do, as I have minus 2 sine of x. And there's my final answer. Now let's talk about dividing two functions. And unfortunately, this rule is a little bit more complicated than even the product rule was. So you have a function f of x over g of x. And in order to calculate the derivative, it's g of x times f prime of x minus f prime of x times g prime of x. That whole thing over g of x squared. And unfortunately, it's not easier than that. And you're just going to have to memorize this rule. Lucky for you, I have a way to remember this. If I think of my function as high over ho, then the derivative of high over ho is ho d high minus high d ho over ho ho. Again, high, ho. Ho d high minus high d ho over ho ho. I know it's silly, but it gives me a way to remember this quotient rule. Let's practice a couple problems. So here we have 3x plus 2 over x squared minus 1. So if I remember my derivative rule, f prime of x, it's ho, the bottom, x squared minus 1, times the derivative of the top, which is 3, minus the top times the derivative of the bottom, all over the bottom squared. Whew, that's a lot. But folks, that's all the calculus there is in this problem. Anything beyond this is going to be algebra. So all we have to do is simplify it using our algebraic rules. So on the top, I'll distribute my 3. Then I'm going to distribute both the negative and the 2x, and I'm kind of going to do that in the same step. And then I'll remember to put that all over my denominator squared. On the top, I still have like terms to combine, but when I do, I end up with the final answer of negative 3x squared minus 4x minus 3 over x squared minus 1 squared. And I'm not going to simplify that down any further than that. All right, next problem. Find the derivative of 2 minus 1 over x minus 1. Now, one of the ways that I can handle this part right here, which I think is the complicated part, is to rewrite that as x to the negative first power. But I get really worried about doing that because I just am concerned that I'm going to make mistakes with that negative sign that's there. So instead, what I'm going to do is I'm going to take this expression, 2 over 1 minus x over x minus 1, and I'm going to multiply it by a form of 1, x over x. And when I do that and I distribute on the top, I get 2x minus 1 over x squared minus x. And I think that's a lot easier to take the derivative of. I could have taken the derivative with that original equation, but the algebra at the end may be a little messy with what I actually have to do. Okay, so now I'm going to take the derivative of that. So I'll have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now I'm just going to simplify it algebraically. So I'll distribute my 2 on the top. I'm going to FOIL those two binomials. I'm going to write that all over the denominator. I will now distribute through my negatives and combine my like terms and end up with a final answer of negative 2x squared plus 2x minus 1 over x squared minus x, that quantity squared. Okay, here's another problem. But be really careful, because just because a problem looks like it's a quotient rule problem does not mean it actually is a quotient rule problem. As a matter of fact, if I simplify this expression algebraically first, it will make my life a lot easier. So what I can do is I can take that negative 3 over 7 right as a fraction in the front, this part, and then I can take my x and I can cancel that out of both of those terms. So I get 3 minus 2x. That's a heck of a lot easier to take the derivative of than the original problem, especially with quotient rule being as complicated as it is. So sometimes you may want to do some algebra up front. So I'll keep that constant there, and then I'll multiply by the derivative of the actual term and end up with 6/7 as my derivative of this function. if you did decide to do quotient rule with this problem, you would get the same answer. It's not magic. It's not like something's going to work one way but not another. It has to work both ways. So if you tried this using the quotient rule, you would still get the same answer. I just believe that this way is easier. And as you know, I'm all about working smarter, not harder. All right, let's talk trig. So, the derivative of the tangent of x. What does trig have anything to do with what we've been talking about so far in this section? Well, we're taking the derivative of tangent of x, which is the same as taking the derivative of the sine of x over the cosine of x. So let's work through this right now. So if I'm taking the derivative of the sine of x over cosine of x, this is in fact a quotient rule problem. All right, and to take the derivative of this, I'd have the bottom times the derivative of the top, which is cosine of x, minus the top times the derivative of the bottom, all over the bottom squared. All right, so on the top, that gives me, let's see here, the cosine squared of x. Ooh, and here a negative times a negative is a positive. And sine, that's sine squared of x, all over cosine squared of x. And I know that sine squared plus cosine squared is equal to 1. So this is 1 over the cosine squared of x, which is in fact the secant squared of x. Holy moly. I don't know about you. I believe it's easier to memorize this rule than it is to go through this process every single time. So here's a list of all the trig rules that I would actually commit to memory. I would know that the derivative of tangent is secant squared. The derivative of secant is secant tangent. We do this very similar to the way we did the other problem if you wanted to prove it. The derivative of cotangent is negative cosecant squared, and the derivative of cosecant is negative cosecant x cotangent x. And again, these proofs are very similar as the way we just proved the derivative of tangent with secant squared. But again, I'm committing these to memory so that I don't have to go through that process every single time I want to take the derivative of one of these trig functions. Let's work through an example. Well, the derivative of 1 minus cosine of x over sine of x. Again, I don't know about this. Would rather not use quotient rule if I don't have to. So one of the things that I will rewrite this as is I will rewrite this as 1 over the sine of x minus the cosine of x over sine of x, using the distributive property of division, and rewriting this problem as the cosecant of x minus the cotangent of x. Then, when I calculate my derivative, the derivative of cosecant is negative cosecant cotangent. And then the derivative of negative cotangent is negative, so we'd have to do the double negative, cosecant squared of x. I think that's a lot easier than using the quotient rule in this particular problem. Again, not that you can't, it's just I think that this process is a little bit easier. Derivatives don't stop with the first derivative. As a matter of fact, we can take the derivative any number of times that we want to. The notation is here on the screen. So you'll see we've been dealing with y prime or f prime of x. The second derivative simply means I'm taking the derivative of the first derivative and getting the second derivative. You'll see y double prime, f double prime of x. Our notation is d squared y over dx squared. That notation is really important. The notation here in this fourth column is the directions for taking the second derivative of f of x. Second derivative of f of x. This is more computer notation in that last column. I don't worry too much about that. The third derivative is taking the derivative 3 times. So coming up with the first derivative, then taking the second derivative, then taking the derivative of the second derivative to get the third derivative. Notation is present here. Once we get to anything more than that, these little marks up here get a lot. So we usually end up putting a 4 in a parenthesis. Notice, if I wanted y to the 4th power, the parenthesis would not be there. But when I put the parenthesis, it's no longer an exponent, It is now the notation for the fourth derivative. This has applications in physics as well. We know that the original function is called the position function, and as we learned last class, the derivative of position is velocity. Well, if we take the derivative of velocity, which is the second derivative of the position function, we get acceleration. So, position, the derivative of position is velocity. The derivative of the velocity is acceleration. Think of it. The rate of change of distance is velocity. The rate of change of velocity is your acceleration. On the moon, the position of an object is modeled by the equation S of t equals negative 0.81 t squared plus 2. Find the acceleration due to gravity. Very straightforward. We'll look at S of t. And we know that in order to get to the acceleration, that is the derivative of the velocity function. And we know in order to get to the derivative of the velocity function, we have to take the derivative of the position function. So, in order to get there, we're going to start with our position function, which is given in the problem, and we're going to take the derivative of that. That, again, gets us the velocity function. So let's see here. That would be negative 0.18 times 2, which is negative 1.62 t. That's the velocity function. To get to the acceleration function, we have to take the derivative of the velocity function. That happens to be the second derivative of the position function. And when we do, we get negative 1.62. The unit of measurement, just so you know, that is actually the acceleration due to gravity on the moon in meters per second squared. All right, folks, that's all I have for you today. This is your homework assignment. I know it's a lot, but I promise we have to practice the quotient rule and the product rule. You got to practice it. You got to memorize it. You got to get it down cold. It will be building on this as we move forward in calculus, and it is very critical you have these memorized. So I apologize in advance for the length of this assignment. I apologize that I'm not with you today to help you through it, but good luck. You got it. I'll see you next time.